OK. Bonjour, welcome. Merci d'être venu. Hi, Adam. So today we are going to see that the retarded Green's function as a spectral representation, just like the susceptibilities. And we will start to really set up the equipment, the concepts that we need to do perturbation theory and compute the real observables and real quantities within specific model. So the first thing would be to go to the interaction representation, and I will show you what it is, and show that the here k is h minus mu n, and this is like the evolution operator, time evolution operator, but in imaginary time. That's the density matrix. And we just like we need to do some sort of perturbation theory where we have when we have quantities that don't commute here, like the kinetic and the potential energy, then it's the same for this. So we will see that it's important. And here, because as you see, when we do this, we are working like the equivalent of imaginary time in some sense. So we will see that and this operator will be called a time ordering operator. I will show you what that means. And consequently, we'll define a Green's function that's different from this one. That is Green's function that's defined in imaginary time. It's called the Matsubara Green's function. And this Matsubara Green's function has some anti-periodicity property that allow us to write it in Fourier series. And we will see that once it is written in Fourier series, then this function and this function are really related, very simply, by analytic continuation. And the tool we will use for that is the Lehmann representation that you already know how to work with. So are there any questions regarding like last time? Okay. So let's so just to see what I mean here by this and what is this A, let us remind ourselves that the retarded Green's function of R prime of t was defined as minus I times the, so that is that remains, it means the trace over quantum states weighted by the density matrix, right? So it's a thermal average of the anti-commutator of psi of RT, psi dagger of R prime 0. Okay, so times theta of t. So I'm lacking here space, unfortunately. So if you compare this with chi retarded, let me just put the I and J here. Just chi retarded of time was equal to 2I times the 1 over 2h bar times the commutator of some operator AI that can be density, current, whatever, and AI of t, sorry. AI of t, A of j, times the theta of t. So you see, with this, what we will do then, we will write that this is equal to minus I times the spectral weight of A of R prime T times theta of T. And clearly the physics is in this. This is just theta function. And we will see that this contains all the spectrum of excitations. And this is the analog definitions that we did here is that we said this is 2I times chi double prime ij of t times theta of t. Okay. So the commutator here became an anti-commutator because we're working with fermions. So you see the analogy, right? A is this, and chi double prime is this. So here it means that if we go to Fourier space, and we know how to do these Fourier transforms, we will have that G retarded of R prime T omega, sorry, go to frequency and then I write time. Bad start. Of omega is equal to integral d omega prime over 2 pi of A of R prime omega prime divided by omega plus I eta minus omega prime. And you should compare this with this here, in this case, was equal to integral d omega prime over pi of chi double prime A ij of omega prime divided by omega prime minus omega plus I eta, right? So you see there was a 2 here, so instead of 2 pi, we have pi. And here there's a minus sign, and here there's no minus sign. So this switches, right? Here you have omega prime minus omega plus I eta, here omega plus I eta minus omega prime, okay? It's just a question of definition. And okay, you can see there's some lack of consistency between these definitions, but we have to live with this, okay, because it's pretty standard. Now, you remember that we had some rules, right? So we have some rules again. If we look at, if you look at the integral d omega over 2 pi of A of R prime omega, what is this equal to? You see A is here, A is this anti-commutator. So if I integrate over all frequencies, it means that I'm looking at time t equals 0, right? Because if I put e to the minus I omega t here, then I should get exactly this. So if I, oh my God, bad start. If I put t equals 0, then it means I'm just looking at this. So it means this is equal to delta of R minus R prime, because that was the value of this anti-commutator when t was equal to 0. Now, the same way I did high frequency expansion here, I can do high frequency expansion. I will get derivative of psi with respect to t, and I will be able to work some rules. Okay, so we're not going to do this today, but I just want you to expect that this happens and not be surprised when you see this. Okay, any questions for this? Okay. So let's move to perturbation theory now, the interaction representation. Interaction representation for the, I see what happens. This is a new type of towel, and apparently it's not as efficient as the previous type. Okay, I have to correct this. Okay. So you see, if you look at the time evolution operator, it's e to the minus I h t. So if you set t equals to minus I beta, you see that this goes into e to the minus beta h, okay? So we will see that for statistical mechanics, we can do everything in this imaginary time. And then if we want observables, depending on what we want, sometimes we get it directly, sometimes we need to do some analytic continuation. So let me work out perturbation theory now, the interaction representation for this object. So if I call u of beta 0, so the imaginary time evolution operator, I write this as e to the minus beta k, where now k is equal to h minus mu n. And in general, h has some h0 plus v minus mu n, where v does not commute with h0. So that's our problem. Okay, potential kinetic energy. So this I will write as k0 plus k1. Okay, and k0 and k1 don't commute with each other. So it means that the evolution operator in the interaction representation, instead of beta, will take some arbitrary imaginary time tau. 0 is equal to e to the k0 tau times u of tau 0. Now we'll write an evolution operator for this. Okay, why do I do that? Normally, you see, I would write d of e to the minus beta h d tau d beta is equal to minus h e to the minus beta h. So if that's the equation of motion, I know this is the solution. So this is why we're working with these derivatives. So if I write the equation of motion for ui, I write d ui d tau will be equal to, so this u of tau 0 is equal to this, e to the minus tau k. So it means that dui d tau is equal to k0 times e to the k0 tau times e to the minus tau k. So this is the first term. I take, okay, I take this, and then there's a term that comes from this derivative, okay? And then I need a term that comes from that derivative. So the term that comes from that derivative will be equal to minus K0 minus K1. Okay, because K is K0 plus K1. So these K0 drop out, and I'm left with this here. So I'm left with minus e to the K0 tau times K1 times e to the minus K0 tau, sort of running out of place, e to the K0 tau times e to the minus K tau. Okay, so this is just UI. So I have UI of tau 0. So you recognize the interaction representation, right? The perturbation K1 here evolves with the unperturbed Hamiltonian. So the equation of motion that I get for UI is dui of tau 0 d tau is equal to minus K1 of tau times UI of tau 0. So what is the solution of this? So if K1 was some constant, this would just be an exponential. Okay? But you see what happens here? I have that this is e to the minus K0 times U. And so this means that the UI is this object here. So it's an exponential, but it's a time-ordered exponential. So we need to work out what we mean by this. You see the problem? Why is it that we cannot write it as just an exponential? So it's discussed in detail in the notes, but in a few words, what happens is that K1 is evolving in time, or imaginary time. So it means that K1 at different times perhaps will not commute with itself. And so when you have the exponential of let's say K0 plus K1, for example, where K1 does not commute with K0, you know that the exponential of a sum is not equal to the product of the exponential. So that's basically the reason, because K1 is evolving with time, so it can be different and not commute with itself. So what is the solution of this? So we want UI at beta. So it means that I will integrate this from 0 to beta. So that will give me UI of beta 0 minus 1, because at tau equals 0, this means that this is 1. So that's the integral from 0 to beta. So here on the right, I have minus the integral from 0 to beta of K1 of tau times UI of tau 0 d tau. Okay? So the way we're going to do this is just like we did in linear response. We solve this iteratively. But in a linear response, all that we did is replace ui here by 1, and that was it. Now we want to do better. So if we want to do better, we can still do it, but by iteration. So the first term, the term linear in K1 is the integral from 0 to beta of K one yes, okay, K1 of tau. And that's it. Okay, I replace ui by 1. Now, if I want to go beyond this, it means that I need to use for ui its first order expression. Or if you want, you take ui and you replace it by this and put it back there. You can see it these two ways, it's the same. So what is the next term? The next term is plus the integral from 0 to beta of K1 of tau. I forgot d tau here, very important. So I have plus, because I have minus minus, integral from 0 to beta K1 of tau. And now I need to put ui of tau here. So ui of tau is this, but just evolved up to tau now, not up to beta. So that's d tau, and that's the integral from 0 to tau of K1 of tau prime d tau prime. You see this? Because here I want ui at tau, so I have to take this, but integrate up to tau only. So d tau prime. Now what takes the next term? The next term will be minus all of this. So 0 to beta times K1 of tau d tau times the integral from 0 to tau of K1 of tau prime d tau prime. But now I need here, what I need is ui at time tau prime. So it means that I have to do the integral from 0 to tau prime of K1 of tau double prime d tau double prime. You see this? And then I continue. So what's happening here? What's happening is that you see this K1 here. If I think of 0 to beta as this, as I increase from 0 to beta, beta is positive. You see that this time tau prime here is always later than this one, tau double prime. And this one here is always later than this one and this one, etc. Okay. Now what I can do is that I can go, you see that if I go from 0 to beta here, and I define a time-ordered product t tau. So this is just an operator that when it acts on things like this, it always puts them in order. En français, c'est le produit chronologique. Okay, time-ordered operator, produit chronologique. So you put it in in time order. Okay, so if I do this, then I have counted things twice because this can be like this or this, so I need to divide by 1 over 2 factorial, which is 1/2. And then here I can continue, I can do the same here. So I can put all of these to beta. And I can define a time order, and then I can let the time ordering operator act on this. And then it will always put them in the right order. What will happen? Well, there are 3 factorial ways of ordering 3 objects. So I'm overcounting 3 factorial ways. So here I have -1 over 3 factorial. And you see that it continues. So that's why I wrote this. Okay, because this, if you expand the exponential in a power series, it will give you exactly this. This plus 1 over 2 factorial times this square plus 1 over 3 factorial times this cube, etc. Okay. So in particular, if K1 is time independent, that just gives 1 e to the minus K1 times beta. So if K0 and K1 commute, then I recover the usual, and K1 is tau independent, which is the same as saying that okay, this here is K1 of tau. So saying that K1 is independent of tau means that it commutes with K0. So I recover e to the minus beta K0 times e to the minus K1 beta. Okay. Do I need to repeat? Don't hesitate. Ask questions if it's okay. If it's not okay. Okay. So I recover all the correct limits. Now let's talk just a few seconds about this time ordering operator. You will see why it is useful. And you see that it works here. I did it in imaginary time, but you can obviously the same thing that applies in the real time. So let us see why this time ordering operator is useful. So suppose that I take the expectation value of a time ordering operator T tau of C1, C of tau 1. This is some destruction operator. Forget about the label. C of tau 1, C dagger of tau 2, C of tau 3, C dagger of tau 4. And now I will, here I just put them in order. Here it's the same, I would put them in order. But here K1 is always quadratic in fermions, so I didn't need to worry about that. But now I'm going to say something here. So in the case of fermion, we add the additional rule that not only does this put in the right time order, but if there is an exchange, there's a minus sign. Okay. So for now, it's just a definition, but it's intimately related to the fact that we had an anti-commutator here in the G retarded. So it's a very useful definition to, or generalization of the time ordering operator to do.
And so this time ordering operator always acts on imaginary times?
No, it acts on any contour, in fact. So for example, I mean, one contour that is used a lot in non-equilibrium statistical mechanics is this one here. And so the time ordering operator can, so this is the imaginary time, that's real time. So for example, this time here is before this time. Crazy, huh? But very useful. So the time ordering operator is defined on a contour, integration contour. So here I defined it in imaginary time, but it's defined on any contour. So if you do this, if you do the same for the for example for u of t0, where t is real time, then you will have some i's that come in, minus I and so on, but everything will be the same and you will be working from 0 to t. And now if you do the same for u of 0t, then things will be backwards. So here I claim that this is equal to minus t tau. And if I permute this in any way I want, so for example, here I just do one permutation, tau 2, c of tau 1, c of tau 3, c dagger of tau 4, then all I need is this minus sign. I've done one permutation. If I do another permutation, for example, I change these two, 4, 3, then I have a plus sign here because I did two permutations. Okay, and I don't need to worry that we are used to the fact that these operators anti-commute. They don't, so we do that, but a C dagger and a C don't always anti-commute. I mean, it's not always equal to minus itself. I mean, if it's at the same time, there's a delta function, right? C dagger is one.
Just before that, you made a mistake. You forgot to exchange the daggers between T4
Forgot to
and
exchange the dagger. Sorry. Thank you. Okay. So normally these, I need to worry. I mean, if it's at the same time, then there's a 1 here. So I can just work it. Inside the time ordering operator, we don't worry about this one. The time ordering operator will always, at the end, when you want to evaluate anything, you need to put things in the right time order. Okay, so the time ordering operator remembers that it needs to be in the same order. So if you have a C dagger and a C that are at the same time, for example, at time tau and at time tau, then inside the time ordering operator, you have to put a little plus here to say that this is infinitesimally later than this one. So it's like that, okay? So if I do this, I know what that is. I can evaluate this. But if I write time ordering operator of this, doesn't mean anything, because the time ordering operator needs to know which time is first. Because if it's this, it's not equal to this in the other order. So I would put a T plus here. Okay. Another useful property of the time ordering operator is this. So suppose that I have a time ordering operator, T tau of e to the alpha c of tau 3, c dagger of tau 2, tau 4, and then I have c of tau 1, c dagger of tau 2. And suppose that I need to take the derivative of this with respect to alpha. By the way, we will do this all the time later. Okay, so that's an important result. And that's another reason why the time ordering operator is important. So this derivative with respect to alpha will behave just like an ordinary derivative. So this is equal to t tau e to the alpha thing times c of tau 3 times c dagger of tau 4 times c of tau 1 times c dagger of tau 2. Okay? And I don't need to worry about anything because the time ordering operator always takes care of putting operators in the right order. So I know it is a sort of an abstract operator. How are we going to do this in practice? So so in practice, many things can be done automatically, but if you're confronted with this, what you do is you put them in the right order. And the reason it's such a useful object, this time ordering operator, is that because we have this shorthand here and we have this property. So it allows us to manipulate things very easily that otherwise would be extremely complicated. And in the end, that's all that we need to have things in the right order. So you see when I differentiate, if the time ordering, if I differentiate this with respect to beta, it behaves just like an ordinary derivative. So I recover the equation of motion that I had for the for this object. Okay, now I'm going to define this Green's function. Okay, why do I define something crazy like this? Well, first of all, notice that I'm just to make things shorter, instead of having g of r prime and write psi of r prime with r prime with parentheses and so on, I'm just doing things more compactly, just because I don't have much space here. So you have to think of this as a creation operator in some basis. For example, in the r basis, it would be psi of r, and this would be psi dagger. Okay, so this is just a shorthand. Now, why do I define this? It will become clear in a second, but let me make a few remarks. First, suppose I want to know the occupation number. I want to know how many particles are in state beta. That's the number operators in state beta. Then you see that this is just a function, and now I have a time ordering operator, so I have to put tau equals 0 minus, so that it goes on this side. And then I get an observable. Okay. Now, I can define Green's functions just like I want. I mean, in the end, as long as I get observables that I need, it's fine. And this is a very useful definition, because in fact you will see that the spectral weight that was so important here, the spectral weight is there as well. It's hidden, you don't see it now, I'm sure, unless you've been exposed to this before. But yeah, the spectral weight is hidden in this thing. So what is this G of alpha beta of tau is equal to minus C alpha of tau C dagger beta if tau is larger than 0, because that's what the time ordering operator is doing, plus C dagger beta C alpha of tau times theta of minus tau. Is it okay? So I'm just using the definition of the time ordering operator here. So explicitly, this is what this is. Now, what do I mean by C alpha of tau? So C alpha of tau is just e to the k tau times C alpha times e to the minus k tau, okay? So it's like the Heisenberg picture for this Schrödinger operator. And what is C dagger alpha of tau? It's equal to e to the k tau times the C dagger alpha e to the minus k tau. Now, why is this a really bad notation? Is this the adjoint of that? Is this the adjoint of that?
Isn't tau a complex number?
No, tau here is real number.
Mm.
So it's not the adjoint, right? Because if you take A, B adjoint, this is equal to B adjoint, A adjoint. And you see that so these, if I really took this like that, then I would have a minus and a plus here. But the reason we do this definition, and it's now just a definition, is because in the end, we want things to be in real time. So if we analytically continue this tau to it minus it, or plus it, I'm sorry, then you see that this is really the adjoint. So it's the adjoint only once it's analytically continued. Otherwise, it's not. Now let's take an example. Let's take an example. And take a k is equal to sum over k of epsilon k minus mu times c dagger k ck. And let me call epsilon k minus mu by definition as zeta of k. Okay. So if I look at the equation of motion for this, so d g alpha beta tau d tau, it's equal to, so the derivative of this is a delta function. What is the derivative of this? Okay, in this case, I have this function, and the derivative is a delta function, and this is this function. The derivative is minus a delta function. Okay? So that means that I have a term that's the anti-commutator of this. So here I will take, with this Hamiltonian here, I will take k as a special case. I will take k, and then when I take the time derivative of k, then I have a first term that is minus a delta function of time, because this is now at equal time, this is just the anti-commutator. And then I get a term that just gives me the time derivative of this object, and we know that the time derivative will be just using this expression will be the commutator of k with c, and the commutator of k with c is minus this object. So I get minus zeta k times g k of tau. Okay. So I took, in other words, there are two contributions to the time derivative. There's this, the delta function, and then there's derivative of this with respect to time. And I know how to compute this because this will be just the commutator of c with k, and given that k is this, I get minus zeta k. Okay. So let's remember this. I will come back to this. I just want to finish with one result, which is that I will go back to alpha beta here. So alpha beta, alpha beta, alpha beta. This result here, which is an anti-periodicity, you see. I want tau to go from 0 to beta, but if tau goes to 0, from 0 to beta, this, in fact, I need it from minus beta to plus beta. But this, I will show you, avoids me a lot of trouble. So if tau larger than 0, I get this. So if tau is larger than 0 by hypothesis, then it means that the Green's function is equal to this, okay? So it means that the g alpha beta of tau larger than 0, tau is larger than 0 by hypothesis, is equal to minus 1 over z times the trace of e to the minus beta k times the c alpha of tau is e to the tau k times the c alpha e to the minus tau k times the c dagger beta. Okay? That's the definition of this average is a trace, and that's the density operator. Now, all that I'm going to use is the cyclic property of the trace. In a trace, I can permute the matrices. I mean, if you don't remember this, you can redo the proof for yourself. This is equal to the trace of BA. Okay? If I do cyclic permutations, then it works out. So, it means that this is equal to minus 1 over z times the trace of, now let me put this completely to the left, okay? So I will write this as C dagger beta, and then I keep the rest. So I have e to the minus beta k, e to the tau k, times the C alpha e to the minus tau k, okay? And I'm at the end. Now let me go put back unity. So that's e to the minus beta k times e to the plus beta k, okay? So this is, by cyclic property, this is 1, okay? So I've recovered the trace. And now what is this guy here? This guy here is equal to minus the expectation value of C dagger B beta times the C alpha of what? Tau minus beta. I have normally, whoops, I erased it, but you know, the evolution operator here has a plus and a minus here. So I have C alpha of tau minus beta. Well, now if tau is positive and is contained between 0 and beta, it means that C alpha of tau minus beta is less than 0. Okay. So it means it is in the right time order here. Tau minus beta is less than 0. So this is before this one, so it's in the correct order. But when it's in that order, I get a plus sign here, normally. Okay. So this is equal to minus G alpha beta of tau minus beta. Okay, which is this equality. Yeah? So I've shown that this function is anti-periodic, in the sense that if I, I change by beta, it changes sign. So because it is anti-periodic, I mean, it means that I can, it will look like this. For example, that's just one example. Let's see, this is 0 here, minus beta, and this is 0. And I can do this, and I can do so you have to flip this, yeah, so it will be like this. Okay, you take a minus sign and you translate it by beta, minus beta. Now, why is there a jump here? Because if here I took an example where we have the same, I should have said, we have the same index here. Alpha, okay. So why there's a jump here because C dagger alpha, C alpha is equal to 1 minus the other one. So this jump here is 1. Okay. And and what is this? This on this side is just this one. So it's the number of particles in state alpha. And this is 1 minus the number of particles in state alpha. And this point here is the same as this one with the minus sign. So it's related also to the occupation. And this is the same as this one. So it's also related to the expectation just with the minus sign. Now, a function that has this property of being anti-periodic, now I will repeat it. I just repeat it like this and like this. And now I will use Fourier series. And the Fourier coefficients, so this is a discrete interval from minus beta to beta, minus beta to beta, minus beta to beta. So if you have a function that is defined on a finite interval, when you do the Fourier series, it gives you discrete frequencies. So for next time, please look at your Fourier series, okay? Because these will be Matsubara frequencies. They will call Matsubara frequencies, but all this is Fourier series. Okay, and you have to be careful because in the Fourier series, what I do is I just take this and I repeat this here. But if you look at the function, the way it's defined here, if you look at this function defined here, it's not equal to that. But fortunately, we need that function only in that interval. So we are free to expand it, like to do this expansion. Okay, so that's a subtlety. Okay, so for next time you look at your Fourier series because it will be useful. And in fact, for the homework, if you look on Moodle, the homework is there. Okay. There are two problems. It's in the next 2 weeks. You have to give it back in 2 weeks. The first problem, I left it in English, and please wait until Monday when I finish here. It will be easier to do the first problem, but it's very easy. Just generalizing to bosons. And the second problem, it's a little bit longer, but there's a French and an English version of the problem, okay? So, but it's the same problem. So look on Moodle, and if you have any questions, you can ask me. Is it okay? Okay, so I'll stop the recording and I'll stay here. If you need, there are further questions, I'm available to answer. Have a good weekend.